Welcome to this lecture. In this lecture, we will discuss how Kubernetes implements DNS in the cluster. In the previous lecture, we saw how you can address a service or pod from another pod. In this lecture, we will see how Kubernetes makes that possible. Say you were given two pods with two IP addresses. How would you do it? Based on what we learned in the prerequisite lectures on DNS, an easy way to get them to resolve each other is to add an entry into each of their etc hosts file. On the first pod, I would say the second pod, web, is at 10.244.2.5, and on the second pod, I would say the first pod, test, is at 10.244.1.5. But of course, when you have thousands of pods in the cluster and hundreds of them being created and deleted every minute, this is not a suitable solution. So we move these entries into a central DNS server. We then point these pods to the DNS server by adding an entry into their etc resolve.conf file, specifying that the name server is at the IP address of the DNS server, which happens to be 10.96.0.10 in this case. Every time a new pod is created, we add a record in the DNS server for that pod so that other pods can access the new pod and configure the etc resolve.conf file in the pod to point to the DNS server so that the new pod can resolve other pods in the cluster. This is kind of how Kubernetes does it, except that it does not create similar entries for pods to map pod name to its IP address as we have seen in the previous lecture. It does that for services. For pods, it forms host names by replacing dots with dashes in the IP address of the pod. Kubernetes implements DNS in the same way. It deploys a DNS server within the cluster. Prior to version 1.12, the DNS server implemented by Kubernetes was known as kubedns. With Kubernetes version 1.12, the recommended DNS server is CoreDNS. We took a brief look at CoreDNS in one of the prerequisite lectures. So how is the CoreDNS setup in the cluster? The CoreDNS server is deployed as a pod in the kubesystem namespace in the Kubernetes cluster. Well, they are deployed as two pods for redundancy as part of a replica set. They're actually a replica set within a deployment, but it doesn't really matter. But we'll just see CoreDNS as a pod in this lecture. This pod runs the CoreDNS executable, the same executable that we ran when we deployed CoreDNS ourselves. CoreDNS requires a configuration file. In our case, we used a file named corefile. So does Kubernetes. It uses a file named corefile located at etc CoreDNS. Within this file, you have a number of plugins configured, the ones highlighted in orange. Plugins are configured for handling errors, reporting health, monitoring metrics, cache, etc. The plugin that makes CoreDNS work with Kubernetes is the Kubernetes plugin, and that is where the top-level domain name of the cluster is set. In this case, cluster.local. So every record in the CoreDNS DNS server falls under this domain. With the Kubernetes plugin, there are multiple options. The pods option you can see here is what is responsible for creating a record for pods in the cluster. Remember, we talked about a record being created for each pod by converting the IPs into the dashed format. That's disabled by default, but it can be enabled with this entry here. Any record that the DNS server can't solve, for example, say a pod tries to reach www.google.com, it is forwarded to the name server specified in the CoreDNS pod's etc resolve.conf file. The etc resolve.conf file is set to use the name server from the Kubernetes node. Also note that this core file is passed in to the pod as a config map object. That way, if you need to modify this configuration, you can edit the config map object. We now have the CoreDNS pod up and running using the appropriate Kubernetes plugin. It watches the Kubernetes cluster for new pods or services, and every time a pod or a service is created, it adds a record for it in its database. Next step is for the pods to point to the CoreDNS server. What address do the pods use to reach the DNS server? When we deploy the CoreDNS solution, it also creates a service to make it available to other components within the cluster. The service is named as kubedns by default. The IP address of this service is configured as the name server on pods. Now you don't have to configure this yourself. The DNS configurations on pods are done by Kubernetes automatically when the pods are created. Want to guess which Kubernetes component is responsible for that? The kubelet. If you look at the config file of the kubelet, you will see the IP of the DNS server and domain in it. Once the pods are configured with the right name server, you can now resolve other pods and services. You can access the web service using just web service or web service.default or web service.default.svc or web service.default.svc.cluster.local. If you try to manually look up the web service using nslookup or the host web service command, it will return the fully qualified domain name of the web service, which happens to be web-service.default.svc.cluster.local. But you didn't ask for that, you just said web service. So how did it look up for the full name? It so happens the resolve.conf file also has a search entry which is set to default.service.cluster.local as well as svc.cluster.local and cluster.local. This allows you to find the service using any name, web service or web service.default or web service.default.svc. However, note that it only has search entries for service, so you won't be able to reach a pod the same way. For that, you need to specify the full FQDN of the pod. Well, that's it for this lecture. Head over to the practice test and practice working with DNS on a Kubernetes cluster. I will see you in the next lecture.
Welcome to this lecture. My name is Mumshad Manambat, and we are going through the Kubernetes certification course. And in this lecture, we will discuss about ingress in Kubernetes. Before we proceed, please remember to subscribe to our channel so that you know when our new videos come out. We will start with a simple scenario. You are deploying an application on Kubernetes for a company that has an online store selling products. Your application would be available at, say, my-online-store.com. You build the application into a Docker image and deploy it on the Kubernetes cluster as a pod in a deployment. Your application needs a database, so you deploy a MySQL database as a pod and create a service of type cluster IP called MySQL service to make it accessible to our application. Your application is now working. To make the application accessible to the outside world, you create another service, this time of type node port, and make your application available on a high port on the nodes in the cluster. In this example, a port 38080 is allocated for the service. The users can now access your application using the URL http://IP of any of your nodes followed by port 38080. That setup works and users are able to access the application. Whenever traffic increases, we increase the number of replicas of the pod to handle the additional traffic, and the service takes care of splitting traffic between the pods. However, if you have deployed a production-grade application before, you know that there are many more things involved in addition to simply splitting the traffic between the pods. For example, we do not want the users to have to type in the IP address every time. So you configure your DNS server to point to the IP of the nodes. Your users can now access your application using the URL myonlinestore.com and port 38080. Now, you don't want your users to have to remember port number either. However, service node ports can only allocate high-numbered ports which are greater than 30,000. So you then bring in an additional layer between the DNS server and your cluster, like a proxy server, that proxies requests on port 80 to port 38080 on your nodes. You then point your DNS to this server, and users can now access your application by simply visiting myonlinestore.com. Now this is if your application is hosted on-prem in your data center. Let's take a step back and see what you could do if you were on a public cloud environment like Google Cloud Platform. In that case, instead of creating a service of type node port for your where application, You could set it to type load balancer. When you do that, Kubernetes would still do everything that it has to do for a node port, which is to provision a high port for the service. But in addition to that, Kubernetes also sends a request to Google Cloud Platform to provision a network load balancer for this service. On receiving the request, GCP would then automatically deploy a load balancer configured to route traffic to the service ports on all nodes and return its information to Kubernetes. The load balancer has an external IP that can be provided to users to access the application. In this case, we set the DNS to point to this IP and users access the application using the URL myonlinestore.com. Perfect. Your company's business grows and you now have new services for your customers. For example, a video streaming service. Now you want your users to be able to access your new video streaming service by going to myonlinestore.com/watch. You'd like to make your old application accessible at myonlinestore.com/where. Your developers developed the new video streaming application as a completely different application, as it has nothing to do with the existing one. However, to share the cluster's resources, you deploy the new application as a separate deployment within the same cluster. You create a service called video service of type load balancer. Kubernetes provisions port 38282 for this service and also provisions a network load balancer on the cloud. The new load balancer has a new IP. Remember, you must pay for each of these load balancers, and having many such load balancers can inversely affect your cloud bill. So how do you direct traffic between each of these load balancers based on the URL that the user types in? You need yet another proxy or load balancer that can redirect traffic based on URLs to the different services. Every time you introduce a new service, you have to reconfigure the load balancer. And finally, you also need to enable SSL for your applications, so your users can access your application using HTTPS. Where do you configure that? It can be done at different levels, either at the application level itself, or at the load balancer level, or at the proxy server level. But which one? You don't want your developers to implement it in their applications, as they would do it in different ways. And it's an additional burden for them to develop additional code to handle that. You want it to be configured in one place with minimal maintenance. Now that's a lot of different configuration, and all of these becomes difficult to manage when your application scales. It requires involving different individuals in different teams. You need to configure your firewall rules for each new service, and it's expensive as well, as for each service, a new cloud-native load balancer needs to be provisioned. Wouldn't it be nice if you could manage all of that within the Kubernetes cluster and have all that configuration as just another Kubernetes definition file that lives along with the rest of your application deployment files? That's where Ingress comes in. Ingress helps your users access your application using a single externally accessible URL that you can configure to route traffic to different services within your cluster based on the URL path. At the same time, implement SSL security as well. Think of Ingress as a layer 7 load balancer built into the Kubernetes cluster that can be configured using native Kubernetes primitives, just like any other object that we've been working with in Kubernetes. Now remember, even with Ingress, you still need to expose it to make it accessible outside the cluster. So you still have to either publish it as a node port or with a cloud-native load balancer. But that is just a one-time configuration. Going forward, you're going to perform all your load balancing, auth, SSL, and URL-based routing configurations on the Ingress controller. So how does it work? What is it? Where is it? How can you see it? And how can you configure it? And how does it load balance? How does it implement SSL? Without Ingress, how would you do all of these? Well, I would use a reverse proxy or a load balancing solution like Nginx or HA proxy or Traffic I would deploy them on my Kubernetes cluster and configure them to route traffic to other services. The configuration involves defining URL routes, configuring SSL certificates, etc. Ingress is implemented by Kubernetes in kind of the same way. You first deploy a supported solution, which happens to be any of these listed here, and then specify a set of rules to configure ingress. The solution you deploy is called as an ingress controller, and the set of rules you configure are called as ingress resources. Ingress resources are created using definition files like the ones we have been using to create pods, deployments, and services earlier in this course. Now remember, a Kubernetes cluster does not come with an ingress controller by default. If you set up a cluster following the demos in this course, you won't have an ingress controller built into it. So if you simply create ingress resources and expect them to work, they won't. Let's look at each of these in a bit more detail. As I mentioned, you do not have an ingress controller on Kubernetes by default, so you must deploy one. What do you deploy? There are a number of solutions available for ingress, a few of them being GCE, which is Google's Layer 7 HTTP load balancer, Nginx, Contour, HA Proxy, Traffic, and Istio. Out of these, GCE and Nginx are currently being supported and maintained by the Kubernetes project. And in this lecture, we will use Nginx as an example. These ingress controllers are not just another load balancer or Nginx server. The load balancer components are just a part of it. Ingress controllers have additional intelligence built into them to monitor the Kubernetes cluster for new definitions or ingress resources and configure the Nginx server accordingly. An Nginx controller is deployed as just another deployment in Kubernetes. So we start with a deployment definition file named Nginx ingress controller with one replica and a simple pod definition template. We will label it Nginx ingress, and the image used is Nginx ingress controller with the right version. This is a special build of Nginx built specifically to be used as an ingress controller in Kubernetes. So it has its own set of requirements. Within the image, the Nginx program is stored at location /Nginx ingress controller. So you must pass that as the command to start the Nginx controller service. If you have worked with Nginx before, you know that it has a set of configuration options such as the path to store the logs, the keep alive threshold, SSL settings, session timeout, etc. In order to decouple this configuration data from the Nginx controller image, you must create a config map object and pass that in. Now remember, the config map object need not have any entries at this point. A blank object will do. But creating one makes it easy for you to modify a configuration setting in the future. You will just have to add it into this config map and not have to worry about modifying the Nginx configuration files. You must also pass in two environment variables that carry the pod's name and namespace it is deployed to. The Nginx service requires these to read the configuration data from within the pod. And finally, specify the ports used by the ingress controller, which happens to be 80 and 443. We then need a service to expose the ingress controller to the external world. So we create a service of type node port with the Nginx ingress label selector to link the service to the deployment. As mentioned before, the ingress controllers have additional intelligence built into them to monitor the Kubernetes cluster for ingress resources and configure the underlying Nginx server when something is changed. But for the ingress controller to do this, it requires a service account with the right set of permissions. For that, we create a service account with the correct roles and role bindings. So to summarize, with a deployment of the Nginx ingress image, a service to expose it, a config map to feed Nginx configuration data, and a service account with the right permissions, to access all of these objects, we should be ready with an ingress controller in its simplest form. Now on to the next part of creating ingress resources. An ingress resource is a set of rules and configurations applied on the ingress controller. You can configure rules to say, simply forward all incoming traffic to a single application, or route traffic to different applications based on the URL. So if the user goes to myonlinestore.com/where, then route to one app. Or if the user visits the watch URL, then route the user to the video app. Or you could route user based on the domain name itself. For example, if the user visits where.myonlinestore.com, then route the user to the where app, or else route the user to the video app. Let us look at how to configure these in a bit more detail. The ingress resource is created with a Kubernetes definition file, in this case, ingresswhere.yaml. As with any other object, we have API version, kind, metadata, and spec. The API version is extensions/v1 beta 1. Kind is ingress, and we will name it ingresswhere. And under spec, we have backend. Now remember that the API version for ingress is extension/v1 beta 1 as of this recording, but this is expected to change with newer releases of Kubernetes. So when you are deploying ingress, always remember to refer to the Kubernetes documentation to know exactly the right API version for that release of Kubernetes. So the traffic is, of course, routed to the application services and not pods directly. The backend section defines where the traffic will be routed to. So if it's a single backend, then you don't really have any rules. You can simply specify the service name and port of the backend where service. Create the ingress resource by running the kubectl create command. View the created ingress by running the kubectl get ingress command. The new ingress is now created and routes all incoming traffic directly to the where service. You use rules when you want to route traffic based on different conditions. For example, you create one rule for traffic originating from each domain or host name. That means when users reach your cluster using the domain name myonlinestore.com, you can handle that traffic using rule 1. When users reach your cluster using domain name where.myonlinestore.com, you can handle that traffic using a separate rule, rule 2. Use rule 3 to handle traffic from watch.myonlinestore.com, and say use the fourth rule to handle everything else. And just in case you didn't know, you could get different domain names to reach your cluster by adding multiple DNS entries, all pointing to the same ingress controller service on your Kubernetes cluster. Now within each rule, you can handle different paths. For example, within rule 1, you can handle the where path to route that traffic to the clothes application, and a watch path to route traffic to the video streaming application, and a third path that routes anything other than the first two to a 404 not found page. Similarly, the second rule handles all traffic from where.myonlinestore.com. You can have path definition within this rule to route traffic based on different paths. For example, say you have different applications and services within the apparel section for shopping, or returns, or support. When a user goes to where.myonlinestore.com, by default they reach the shopping page. But if they go to exchange or support URL, they reach a different backend service. The same goes for rule 3, where you route traffic to watch.myonlinestore.com to the video streaming application, but you can have additional paths in it, such as movies or TV. And finally, anything other than the ones listed here will go to the fourth rule, that would simply show a 404 not found error page. So remember, you have rules at the top for each host or domain name, and within each rule, you have different paths to route traffic based on the URL. Now let's look at how we configure ingress resources in Kubernetes. We will start where we left off. We start with a similar definition file. This time under spec, we start with a set of rules. Now our requirement here is to handle all traffic coming into myonlinestore.com and route them based on the URL path. So we just need a single URL for this, since we are only handling traffic to a single domain name, which is myonlinestore.com in this case. Under rules, we have one item, which is an HTTP rule in which we specify different paths. So paths is an array of multiple items, one path for each URL. Then we move the backend we used in the first example under the first path. The backend specification remains the same. It has a service name and service port. Similarly, we create a similar backend entry to the second URL path for the watch service to route all traffic coming in through the watch URL to the watch service. Create the ingress resource using the kubectl create command. Once created, view additional details about the ingress resource by running the kubectl describe ingress command. You now see two backend URLs under the rules and the backend service they are pointing to, just as we created it. Now, if you look closely in the output of this command, you see that there is something about a default backend. What might that be? If a user tries to access a URL that does not match any of these rules, then the user is directed to the service specified as the default backend. In this case, it happens to be a service named default HTTP backend. So you must remember to deploy such a service. Back in your application, say a user visits the URL myonlinestore.com/listen or eat, and you don't have an audio streaming or a food delivery service, you might want to show them a nice message. You can do this by configuring a default backend service to display this 404 not found error page. The third type of configuration is using domain names or host names. We start by creating a similar definition file for ingress. Now that we have two domain names, we create two rules, one for each domain. To split traffic by domain name, we use the host field. The host field in each rule matches the specified value with the domain name used in the request URL and routes traffic to the appropriate backend. In this case, note that we only have a single backend path for each rule, which is fine. All traffic from these domain names will be routed to the appropriate backend irrespective of the URL path used. You can still have multiple path specifications in each of these to handle different URL paths. Now let's compare the two. Splitting traffic by URL had just one rule, and we split the traffic with two paths. To split traffic by hostname, we used two rules and one path specification in each rule. Well, that's it for this lecture. Let us now head over to the practice test section and practice working on ingress. Now there are two types of labs in this section. The first one is where an ingress controller, resources, and applications are already deployed, and you basically view and walk through the environment. The first one is where an ingress controller, resources, and applications are already deployed, and you basically view and walk through the environment, gather data, and answer questions. Towards the end, you would create or modify ingress resources based on the needs. In the second practice test, you will be deploying an ingress controller and resources from scratch. Well, good luck and hope you enjoy the labs. I will see you in the next lecture.